transformation of graphs. This is really helpful in conjunction with your graphing calculator to help you predict what a graph is going to do and then what would be the appropriate window to use as you're trying to graph the function on your calculator. So I'm going to look at a few functions here to start with. F of x equals x squared is our basic parabola, and I've graphed it on my calculator here. And then I'm going to look at f of x subtract 2. So I'm taking this function, subtracting 2 from it, and that would give me the function x subtract 2. And that gives me this graph. And then let's go ahead and look at our next graph, f of x plus 5. So our basic graph with a constant 5 added to it will be x squared plus 5. Looks like this. So what's happening with these three graphs? It's the same basic function, but it's being slid up and down. This function looks just like this function, but every y value is 2 values lower than it is on the basic function. In this parabola here, every y value for a given x is a value of 5 higher than it was on the original function. So comparing the graphs of f of x and f of x plus a constant, the graph of f of x is being shifted vertically up or down by the value of c. Now we're going to look at the absolute value function. F of x equals the absolute value of x. I've graphed it on my calculator. You can find the ABS function on your calculator by hitting math, cursor to the right once under num, and then you should see the ABS. And now I'm going to compare this function to f of x plus 4. So inside the function, inside the absolute function, I'm going to be adding 4 directly to the value of x, then performing the absolute value function afterwards, after the addition. And that would give me this graph, absolute value, parenthesis, x plus 4, close parenthesis. Looks like this. And then, oh, sorry, that's a little hard to see there. F of x subtract 1, absolute value of x subtract 1. Again, the subtract 1 is being performed on the x first, and the absolute value function is occurring afterwards. So comparing the graphs of f of x and f of x plus c, where the plus c is inside the function, the graph of x is being shifted horizontally, left to right by the value of c. You want to be a little bit careful with the horizontal shifts because they don't go the direction you might think they would at first. The x plus 4 shifts the graph left 4. The x subtract 1 shifts the graph to the right 1. So this one goes the opposite direction you might think of at first. Okay, now we're going to look at some stretching. So we're back to our basic parabola, f of x equals x squared. And I'm going to look at 4 times the function. So here we're multiplying by a constant. And I get this long, skinny parabola. And then I'm going to compare this to 1/2 f of x, 1/2 x squared. And I get this shorter, wider function. So what happens here is it's being stretched or compressed vertically by a multiple of c's. It's kind of like we grabbed the edges of the function and grabbed it taller. And here we made it shorter. In the long run, it's going to be a lot easier to think of these as taller and shorter rather than narrower and wider. Just a little bit easier to keep track of things. Think of it that way. So it's a vertical stretch or vertical compression. If you multiply by a value larger than 1, you'll get the taller graph. Multiply by a value between 0 and 1, you'll get the shorter graph. Okay. Now, what I'm going to use for my basic function is x plus 4 squared. So that's this parabola here. And I just wanted something that was off-center for this particular example. And what I'm going to do is multiply it, the whole function, by a negative 1. So negative x plus 4 all squared gives me this upside-down parabola. And now if I go inside the function and change the x with the negative x, I get this function suddenly popped over here to the right. So what's happening here, if you take a negative times the whole function, the graph's reflected over the x-axis. It's flipped over the x-axis. It's flipped upside down. Whereas if we go inside the function and replace the x or x values with the negative x values, the graph is going to be reflected over the y-axis, reflected over here. So it's rotated over sideways. Okay, now what if we have a combination of some transformations? So here's our basic square root of x. So the first function I'm going to look at is 3 times the function, and then x plus 1. So inside the function, I'm adding 1 to x, and then I'm taking the whole function times 3. So that gives me 3 times the square root of x plus 1. So I can see the function's got a little taller, and it's also kind of floating over here. Then negative f of x plus 2, it's flipped over, and it's shifted up. F of negative x subtract 4, so I'm replacing the x with negative x, I'm subtracting the 4, so that would be the square root of negative x subtract 4. And a couple things have happened here. It's flipped over the y-axis, and it's also down 4. And the order here is important, so let's step back a minute and talk about that. So the order of transformation follows the order of operations. The first thing that happens physically to the graph are any horizontal shifts, because those are inside the function, so anything that shifts it left to right. Then there's going to be the reflections, because those are multiplications. Next, we'll have any vertical stretches or compressions, so that's still a multiplication operation. And then last, what's going to happen are the vertical shifts, which happen outside the function, and that's the shifting it up and down with addition and subtraction. So for that first one we looked at, the negative f of x plus 2, the graph would first reflect over the x-axis, that'd be the negative times f of x, and then second would shift up 2 units. For f of negative x subtract 4, inside the function, we have the negative x, so the graph would first reflect over the y-axis, that rotation over around the y-axis, and then shift the whole thing down 4 units. And then for 3 times f of x plus 1, 3 times the square root of x plus 1, inside the function we're first adding the 1s, would first shift horizontally left 1 unit, and then would stretch vertically by the factor of 3, getting at that taller graph. So each y-coordinate would be 3 times as large, both positive and negatives, but any x-intercepts don't change. Okay, let's look specifically comparing f of x equals x squared, and the rotation would get with f of negative x equals negative x squared. So graphing x squared and negative x squared, we only see one function. That's because they're right on top of each other, they're identical function. The graphs are identical because x squared has what we call symmetry to the y-axis. It's what we often call an even function. If you flip the graph over the y-axis, rotating it this way, it matches the original function. So anytime, if you can go into a function and replace an x with negative x simplified, and you still have the original function, that's what would happen here. Negative x squared is just x squared. Then that f function is what we call an even function. It's symmetric to the y-axis. If we fold it on the y-axis, we'd have a mirror image. Also, if we took the f of negative x and we got the exact opposite, the rotation over the x-axis, then f is what we call an odd function. We call that being symmetric to the origin. So what does odd look like? Here are a couple odd functions. I think it's easiest to think of it, take the function, flip it over the x-axis, flip it over the y-axis, and then it matches exactly the original piece. So take one piece, flip it over this way, flip it over this way, and we get that mirror image. So the following even, odd, or neither. So f of x equals x cubed plus x. If we replace the x values with negative x, simplify, a negative cubed is still negative, negative x is negative x, factor out the negative, and we get the exact opposite of the original function. This is a negative of the original f of x. So this would be an odd function. For f of x is the absolute value of x plus 2. Replacing the x with negative x, the absolute value of negative x is just x. So this f of negative x is equivalent to the original function f of x, and it's what we call an even function. In this example here, replacing the x's with negative x, the negative x squared is positive x squared, negative x is negative x, and this does not equal the original function, nor is it the opposite of the original function, so this, like most function, is neither even nor odd. And then let's take a quick look at their graphs. So the odd function has that symmetry to the origin, the even function is symmetric across the y-axis, and the neither function just doesn't have any symmetry.